Jai Hind and good morning. I am Professor Devendra Singh, and today I am going to discuss about some basic concepts of strength of material. This will be very useful for mechanical engineering students and the BTech first year fundamentals of mechanical engineering students. So, and it is going to be very interesting topic today. So, everyone of us are well aware about the Hooke's law. The Hooke's law states the relationship between the stress and strain. That is, stress is directly proportional to strain. So it is applicable to the limit of stress strain up to which there is a relationship. So if I say Hooke's law is valid up to the elastic point, it is accepted, but more precisely, the Hooke's law is valid up to the proportionality limit, because there is a linear relationship between stress and strain. So if I wish to write the relationship between stress and strain, so I use sigma for the normal stress and epsilon for the normal strain. According to Hooke's law, this is a proportionality limit. So this is Hooke's law. And if I want to convert this proportionality sign into equal, I have to introduce one constant of proportionality, that is normally indicated or signified by E epsilon. All of us are well aware and the relation is well known to us. Now this proportionality constant is the property of material, and we call this is elastic constant of materials. Elastic constants of materials, right? Constants of materials. Now engineering materials, right? Now I wish to introduce how many elastic constants for the materials are useful for mechanical engineers and engineering students to be aware about. There are four elastic constants. One is the modulus of elasticity. Modulus of elasticity. This is first. Our base topic for this discussion or for this lecture is the elastic constants. So I am briefly discussing about the elastic constants here. Modulus of elasticity, then shear modulus. Shear modulus. Then third one is the bulk modulus. And fourth one is the Poisson's ratio. Poisson's ratio. And we generally use these letters to signify modulus plus is capital E, shear modulus is capital G, bulk modulus we use K, capital K, and Poisson ratio by mu. These are the four elastic constants for any material, four elastic constants. So if you want to define these elastic constants, we will use this Hooke's law, right? If we are using the shear stress tau, and according to Hooke's law, the shear stress is directly proportional to the shear strain, then tau is equals to G phi Here G is again the proportionality constant, and we say this G is tau upon phi, that is shear stress upon shear strain, shear stress upon shear strain. I should write it here, shear stress upon shear strain. As modulus of elasticity, E, you can write E is equals to sigma upon epsilon. It means this is normal stress upon normal strain. Now, the third one is the bulk modulus. So, bulk modulus is K is equals to sigma upon epsilon V. This is normal stress in any direction divided by volumetric strain, right? And Poisson ratio, the fourth one is the Poisson ratio. I write nu is equals to lateral strain upon longitudinal strain. This is Poisson ratio. This is G, shear modulus or modulus of rigidity. This is bulk modulus, and this is the modulus of elasticity. These are the primary basic definitions of these four elastic constants. Next is the relationship between the elastic constants. So, I start with first case, the relationship between E, K and nu. This is a very simple. If I want to establish the relationship between modulus of elasticity, bulk modulus and Poisson ratio, what I will use a cube. It is subjected to 3 hydrostatic state of stress. This is sigma, this is sigma, this is sigma, this is sigma, here it is sigma, here it is sigma. 6 stresses, in fact 3 stresses are subjected. One is action, other one is the reaction, and I consider, suppose this is x-axis, this is y-axis, this is z-axis. So, I will consider the epsilon x is the strain. This is longitudinal strain or the normal strain in x direction. Epsilon y is the strain in y direction. Epsilon z is strain in z direction, right, caused by sigma in x direction alone. And if these three are acting simultaneously, then the Poisson ratio will play its role to affect the net strain in the x direction and y direction. So the net strain in x direction is net strain epsilon x minus nu times of epsilon y minus nu times epsilon z. If epsilon x, epsilon y, epsilon z, all the three are of same nature, then this is the relationship between the net strain caused by sigma x, sigma y, sigma z in the x direction. So in the case of hydrostatic state of stress, sigma x, sigma y, sigma z, they are equal in magnitude. Sigma is equals to sigma x is equals to sigma y is equals to sigma z. Modulus of elasticity is the property of the material. So I can write within the elastic limit, this is sigma upon E, that is sigma x upon E, and sigma x is equals to sigma minus nu times sigma upon E, that is sigma y upon E. Sigma y is equals to sigma minus nu times sigma upon E, that is sigma z upon E. So net strain is sigma upon E minus 2 nu sigma upon E, that is equal to sigma upon E into 1 minus 2 nu, that is epsilon x. Now I want to write epsilon y net. Epsilon y net similarly can be easily written here, sigma upon E minus nu sigma upon E. This is sigma y upon E. This is sigma z upon E minus nu times sigma x upon E, that is sigma, is equals to sigma upon E minus 2 nu sigma upon E in case of hydrostatic state of stress, that is sigma upon E 1 minus 2 nu. And similarly, epsilon z in the z direction, that is equal to sigma upon E 1 minus 2 nu. It should be noted, this is the case when the cube is subjected to hydrostatic state of stress. Now I want to find the volumetric strain. So in case of volumetric strain, epsilon V, this is V, volumetric strain, is equals to epsilon x net plus epsilon y net plus epsilon z net. I will prove how is it, but it is the well established relationship for volumetric strain. So you can write this is sigma upon E 1 minus 2 nu plus sigma upon E 1 minus 2 nu. This is sigma upon E 1 minus 2 nu. This is epsilon V. So we can write this is 3 times sigma upon E 1 minus 2 nu is equals to epsilon V. Now I write this E is equals to 3 times, E is equals to 3 times sigma upon epsilon V 1 minus 2 nu. So by definition, this normal stress upon volumetric strain is nothing but it is the bulk modulus of the material. So the relationship between modulus of elasticity and the bulk modulus is E is equals to 3K 1 minus 2 nu. Done. This is done. Now, I tried to establish this relation. Whether this is valid or not. So, I will prove it. Consider a cube having the dimension x, y and z. X, y and z. This is a cube. This is x direction. This is y direction. This is z direction. So, initial dimension is this is z, this is x and this is y. So, what is the volume? Volume of the cube is x, y, z. This is initial volume. Initial volume. Now, it is subjected to some kind of stresses. It is subjected to some kind of stresses, sigma x in the x direction, sigma y is the sigma z direction, sigma y direction and sigma z in the sigma z direction. All it is subjected to some kind of load which will cause the change in the direction. In x, there is a delta x is the change in dimension along x direction. Delta y is the change in the dimension along y direction. Delta z is the change in dimension along z direction. So, the final volume means V plus delta V is nothing but it is the product of final dimensions and y plus delta y and z plus delta z. What it will be? The product will be xyz plus xy delta z plus yz delta x plus zx delta y plus delta x delta y z plus delta y delta z to x plus delta z delta x y plus delta x delta y delta z. I think this is the perfect product xyz xy delta z yz delta x zx delta y delta y z delta x delta y z delta y delta z x plus delta and so on. So, this cube is made of some rigid material. So, in case of the rigid material, the change in the dimension is very small. So, what we will do? We will ignore the product of two or more smaller quantities. So, we can say Vf can be written as xyz plus delta x yz plus delta yzx plus delta z xy. and the change in volume delta V is Vf minus Vi initial. If we subtract this from this, what we will get? We will get delta X YZ. This is product. This is product. So I should use like delta X multiplied by YZ plus delta Y multiplied by ZX plus delta Z multiplied by XY. This is the change in volume, and by definition of volumetric strain, that is epsilon V is equals to volumetric strain is equals to change in volume upon original volume. So epsilon V, I can write delta V upon V, that is equal to delta X into YZ plus delta Y into ZX plus delta Z into XY divided by XYZ. This will come out delta X upon X plus delta Y upon Y plus delta Z upon Z, and this delta X upon X is nothing but it is the change in the dimension along the x-axis to the original dimension in the x direction. This is the ratio that is known as the strain along the net strain along the x direction. So what is epsilon V? This is epsilon x, that is delta x upon x, net strain along the x direction, plus epsilon y, that is the net strain along the y direction, plus epsilon z, that is the net strain along the z direction. And this relation I have used to establish the relationship between modulus of elasticity with Poisson ratio and the bulk modulus, and that is that relationship I have established, that is E is equals to 3K 1 minus 2 nu. I think you have enjoyed this lecture. In the next lecture, we will establish the relationship between the modulus of elasticity, shear modulus, and the Poisson ratio. That will be a very interesting and very enjoyable video will be. So we will meet again. So thank you very much for this session. Good luck. Bye bye.